Okay, we just finished up the series on pharmacokinetics. Pharmacokinetics asks, what does my body do to the drug that I just take? Pharmacodynamics asks the question, what does the drug do to my body? And so this encompasses things like mechanism of action of the drug. It also encompasses things like mechanism of toxicity of the drug, the toxic dose, the therapeutic dose. These are all things that are covered in pharmacodynamics. Now, mechanism of action, mechanism of toxicity, clinical use of a drug, these are all dynamic pharmacodynamic topics that are considered drug-specific. So drug-specific. I'm not going to cover anything drug-specific in this video. What I'm going to cover is the basis of understanding for all of the other pharmacodynamic things that you're going to learn about on specific drugs. Now in the last video we talked about that the clearance in the liver follows Michaelis-Menten enzyme kinetics. And that's because the medication is broken down by enzymes. It's broken down by the enzymes of the P450 system. But did you know also that drugs, most medications, have an effect on the body by interacting with enzymes and receptors? It may have an effect by interacting as an enzyme activator, as an enzyme inhibitor. There's several different ways, and so we can model the effect of a medication most of the time using these same Michaelis-Menten kinetics. And just to remind you, this is a diagram showing a Michaelis-Menten enzyme graph. Now in this, I've changed this graph, and what I've done is I've kept the V, the velocity of the reaction, the same. What I've done is I've taken the x-axis and I've converted it into the log of the x-axis. So you remember the x-axis represents the concentration, the y-axis is the reaction rate. So this is a log concentration graph. Here I've showed two graphs where the Vmax has been reduced, but the Km is the same. And this is actually difficult to see on this particular graph, so I'm going to exaggerate it a little bit. I'm going to go ahead and draw, this is my graph, and then I'm going to have another graph where I'm going to start out at time 0 again. I'm going to change the color to green, and I'm going to graph this as a reduced Vmax. Now if I were to estimate where where I reach about half of my Vmax, I would say that would be about right here. And over here, if I were to estimate where I am at about half of this Vmax, I would say that it would be about right here. Now you can see that the concentration at half of Vmax is the same. So when concentration is half of Vmax, that's Km. So Km for both of these are the same. Simply the Vmax has been reduced. And you can do the same thing with the curvy looking graph, where you can say that I can come to about half right here, and this one looks to be about half of right here. And I didn't draw it perfectly, but if we can imagine that it was drawn perfectly, then my Km would be the same. Now in this graph, Km is switched from 25 to 100. Vmax is the same. You say, well, wait a second, Vmax doesn't look like it's the same. What actually is, this would have to continue out a little bit further in order to reach actual Vmax, and the same thing for this one. And so this is where we get to the effect, the effect of the of the enzyme. So if we get 100% of the reaction rate, if we're talking about medication binding to a receptor, if that receptor is 100% bound all of the time, then you will have 100% of the effect of the receptor. Now here what we've done is we've modeled two different drugs. These drugs act on the same receptor, but they have an obvious difference. They have a different, look at where you have 50% of the reaction rate, we call that Km. It's 50% of the reaction rate, it's called Km. And you can see that the Km of these, the Vmax is the same. If you add enough of either drug, you'll get the same maximum effect. But the Km is different. So where you get 50% of the effect, This value, or this concentration, is also called the potency. So Km in this situation is just another term for potency. And another way to put it is to say that the potency is equal to the reciprocal of EC50. So let's just give some imaginary numbers. This one is 10 and this one is 15. Well, we can see that you get that EC50 much earlier with this first blue drug, and so its potency, it has a higher potency, but it reaches that at a lower value, so we would say that the potency is equal to 1 over 10 for this one, and it is equal to 1 over 15, or a much lower number, for the second drug. And so if we say that the potency is equal to the reciprocal of the EC50, then you're going to always see that the lower number has the higher potency. On this one, I mapped it out so that both have the same EC50, but it's obvious that this blue drug has a much higher maximum effect. So the efficacy, it defines the ability of a drug to cause an effect when it is bound to the receptor. So EC50, it describes how well the enzyme binds to the receptor, and the Emax, or the efficacy, defines how well an effect is driven by binding. So we're already assuming that there's something bound, and we're saying, okay, there's something bound. How much of an effect do I get when there's something bound? Is it always going to cause the receptor to be activated, or will it only cause the receptor to be activated most of the time, or some of the time, or half the time? This is called efficacy. Now, efficacy typically is considered way more important than potency. Here I've graphed two drugs, so you can see that the efficacy of this blue drug is much, much higher, and the potency of this yellow drug is much, much higher. So I would say EC50 is about right here versus about right here. So if we called this a 5 and called this a 10, then 1 over 5 would be the potency, 1 over 10 would be the potency here. You can see that it has a higher potency, almost double or exactly double. But the efficacy is, the Emax is about 80%, and this one is at 100%. If I'm talking about something that is going to block pain, let's suppose I'm getting a surgery on my arm, and I'm looking at a drug that is going to block the sensation in my arm during that surgery. I don't want something that's going to work 80%. I don't want to feel 20% of the knife cutting into my arm. And so you can see how efficacy is considered to be far more important than potency. In fact, things that are highly potent tend to have a very low therapeutic index. So we've got this term, I've added a new equation here. We've got this term dissociation constant. Now, dissociation constant, if we think of enzyme kinetics, Michaelis menten, as Km, the constant, this constant says how well does my enzyme and substrate bind to each other? How well do they meet up with each other, and what is their affinity for each other? On the other hand, dissociation constant is like the inverse of that. How well do they leave each other? And so you can see that as my drug concentration increases to where it's far above Kd, then this term reduces to the drug concentration. So when the drug concentration is really, really high, then I get an equation of 1 over 1, or any number over itself is equal to 1. That means that this ratio would also have to equal 1. And so as the drug concentration goes up really high, the effect approaches the maximum effect. Okay, previously we were looking at two different drugs having different effects. Now what I'm going to look at is the same drug, in that it can have a therapeutic effect, or it can have a toxic effect, and that's going to depend on the concentration. And so when we define the therapeutic effect, the EC50, I'm asking the question, at what point does 50% of the population have the therapeutic effect? So at this specific dose, 50% of the population gets a therapeutic effect. And then I get to my toxic dose, my TD50. TD50 asks the question, at what dose does 50%, or at what concentration does 50% of the population experience a specific side effect, a specific toxin? And so that would equal right here. And so my therapeutic index is the ratio of these two numbers. Therapeutic index would be the TD50 divided by the EC50. Toxic dose for 50%, effective concentration for 50%. Therapeutic window, on the other hand, is the range of concentrations that can effectively treat a disease without causing an adverse effect. Now, I haven't drawn this in perfectly well. You see there's a little bit of some of the people are going to experience a toxic effect at this dose, and over here a lot of people are not going to experience treatment, but I've just drawn this in just so you can have a visual of what the therapeutic window is. The therapeutic window is a range, whereas the therapeutic index is a ratio. Now let's talk about agonism. So you have agonists and antagonists, or inhibitors. So let's look at, you can have something be a full agonist. That means at some concentration you will get 100% of the effect. You can have a partial agonist, so that at an infinite concentration, if we brought our concentration of this drug up to infinity, the effect would only be some amount less than 100%. Now there's this thing called inverse agonist, and what that means is I have this enzyme, this thing, and it has a basal level. At base, it runs a specific reaction once per hour. If I add an agonist to it, it will go and it will run that reaction 1,000,000 times per hour. But I can also add my inverse agonist. Inverse agonist means that you get a response below base level. So from 1 time per hour, I would go down to 1 time every 10 hours. And then you have neutral agonists, which maintain status quo. Now, neutral agonists are the same thing as inhibitors. A neutral agonist is just another name for an antagonist. Inverse agonist is not the same thing as an antagonist. Inverse agonist is an antagonist that is also acting on something that has a basal activity. Examples would be the GABA receptor. GABA has a basal level of activity without any activation from its agonist at all. Naltrexone and naloxone, these act as partial inverse agonists on opioid receptors. So there's your pharmacology for that. Most antagonists you're going to work with are either going to be competitive or non-competitive. So you gotta have agonists. We just talked about those. Now we're talking about antagonists. Antagonists will either be competitive or non-competitive. There are a few other subtypes, but we're not going to get into those. They're not very high yield. There's not a lot of things that model them. But you are sure to be asked about competitive and non-competitive antagonists on the USMLE Step 1. So let me go ahead and explain what that is. Let's suppose I have 3 receptors. These are 3 receptors, enzymes, whatever that you want them to be. And you have a bunch of inhibitors. We'll make the inhibitors this red color. You have a bunch of inhibitors just floating around. This kind of looks like smiley faces now. And you have just this one agonist. This agonist is a natural agonist. It's in your body. And if it had free access, it would bind to one of these 3 receptors. Its problem is it can't. The receptors it tries to bind to, it's already being bound. Its place has already been taken up by some antagonist. So I went ahead and made my agonist a little fancier. I'm going to add a whole bunch of agonists. I'm going to have a whole bunch of agonists. And when I do that, what you're going to see is that my agonists are going to be so high that now they are binding to the receptor instead of the antagonist. The antagonist can't bind to it anymore. Whenever my substrate concentration gets really, really high, it doesn't matter that I have antagonists there, it's still going to reach the maximum binding, the Vmax. And so I've tried to model that for you and to say that in this blue line, we see the normal activation of some enzyme or some receptor by its agonist, and that as the agonist concentration increases, it approaches Vmax. But we see that with an inhibitor present, we've added a specific concentration of inhibitor, and that with that present, now it takes longer, but if we keep adding more and more substrate, eventually we do still get back up to Vmax. Because eventually we will outcompete all of the agonists, or all of the antagonists. So first we looked at competitive antagonists, and so we call them competitive because the substrate and the antagonist can compete for the binding site, and whoever has the most strength wins. Now we're going to look at non-competitive. So I have my antagonist right here, and it binds to this site over here, but my agonist binds to this site up here. Now the problem is, whenever the antagonist is bound here, the enzyme is not free to do anything, so it's just stuck. It has no activity. It doesn't matter if it's completely bound by the substrate or not. Now this one over here, it doesn't have any antagonist bound to it, so it can still have activity. This one agonist over here can still have activity. And so it's basically like when I have a non-competitive antagonist, it's basically like I have decreased the constant my enzymes. I have fewer enzymes. Now you'll remember that the Km of an enzyme, the Michaelis constant, it is a constant that describes the enzyme itself. It also describes the group of enzymes together. So I can say that my Km in this situation has stayed the same, but I have taken most of my enzymes out of commission, and so my Vmax has decreased. And so that's the most important things you need to know, is that with non-competitive antagonists, Vmax is reduced and Km is the same. With competitive antagonists, Vmax is going to stay the same, but Km will appear to be altered. This is called the apparent Km. Now you already know you can map on a log concentration curve, and you get this curve kind of like this. And you know you can graph things on a concentration curve, and you get a graph that kind of looks like that. That's called the Michaelis curve. But there's another way to graph called the Lineweaver-Burk. It's sometimes also called the double reciprocal, and that way of doing it is that you have your 0 point right here, and your line is going to look like this. And so what you have right here is 1 over the velocity, and on this graph you're graphing 1 over the substrate concentration, and your slope is going to equal Km over Vmax. At this point right here you have 1 over Vmax, and at this point right here you have negative 1 over Km. Now if you were told that somebody added an inhibitor and it changed the graph to this, you would see that negative 1 over, so your Km has stayed the same, but your Vmax has changed. This would be considered a non-competitive inhibitor. On the other hand, you might have a graph that looks like this. This, you see that the Vmax has stayed the same, but Km has changed. This would be a competitive inhibitor, because competitive means that at some concentration you can compete enough that you reach your normal Vmax. Now there's something called irreversible antagonists, and the reason I'm bringing this up is because you're going to find a lot of irreversible antagonists, and theoretically, if you have a bunch of enzymes that are saturated, or a bunch of receptors that are saturated, the enzyme, the substrate, the drug, it binds to that receptor irreversibly. It binds in there and it never moves away. Theoretically, you should have completely no enzyme activity, no receptor activity in the body if you bind everything with irreversible antagonists. But sometimes when we do that experimentally, we bind everything we can find with irreversible antagonists, there's still, whenever we add then we come back in and we add in an agonist. When we do that, we have some activity. The agonist has activity, and the way we explain that is that there were spare receptors. They were hidden somewhere. Maybe they were in endosomes, and as soon as all the receptors got bound up, it moved those endosomes back out to the surface. There's a bunch of different models for how spare receptors work, but we just call that the spare receptor theory. So the last thing I'm going to look at here with you is whenever you have a full agonist, so we've got a full agonist, we've got a partial agonist. A partial agonist can act as an antagonist to a full agonist. So what I mean, here I have modeled my full agonist, the effect, the response of my full agonist. So I've given a full agonist up until it reaches 100% of its maximum response. And I keep that concentration the same, and I slowly start adding partial agonist. So the partial agonist is increasing. And what is happening to the overall effect? The green is mapping the overall effect, the effect due to the full agonist plus the effect due to the partial agonist. It's mapping it out right here. And what you see is that as you increase the dose of the partial agonist enough, eventually the overall effect is going to equal the effect due solely to the partial agonist. The partial agonist is going to become a competitor. It's going to compete for the receptor with the agonist. And whenever it hits that receptor, it will only give part of a response. So we can think of it like this. So imagine that this is my receptor, and if I had a perfect full agonist, it would fit in here like this, and as soon as that thing gets fully fitted in there, every time it causes a response to shoot down. But the affinity, we're not even talking about the affinity, but let's just say it has a high affinity for that as well. On the other hand, I might have a drug that looks like this, and it goes in here and it binds with the same affinity, but because it doesn't hit, let's say that there's some sort of a button right here, because it doesn't fully hit that button every time, it doesn't always cause a response. It only causes a response half the time. This is what we would call a partial agonist. It has an effect part of the time. Partial agonist does not say anything about the affinity, so this could have a lower affinity or a higher affinity or the same affinity as the full agonist. What we're saying is the effect that we get. So here I've went ahead and written this out. There's the total receptor activity, activity due to the full agonist, activity due to the partial agonist. And with that, that is your introduction to pharmacodynamics.